Okay, so we are going to take a look at what you've been working on. And so what I'm going to have you do is each one of your teams, I've shared a little space on my screen. And so each one of the teams in that space, I want you to write the equation dy dt equals f of t, right? What you came up with that would produce the slope field that we're interested in.
Do you guys want me to write mine, what I came up with?
Go ahead, because I'm not sure I got mine right.
Just the equation, you don't have to draw the graph. So for example, for each one of the teams, fill in the blank. Give me an equation that should produce the slope field that we want.
That color is horrible.
Can we just assign like random values?
Yeah, absolutely. Yeah, I didn't give you any numerical values for the t values, so yeah, you have to. Yeah. And you can handwrite it or you can type it in. If you want to type it in, that's fine too. Okay, so far so good. Man, I'm having trouble reading that blue. Makes me wonder whether I can I change the font color? I don't know if I can change the font color. I don't think
I've been trying to fix it, and it's like it won't let me click on it again. So maybe I'll just retype it for you.
Yeah, I wonder if, under format, if you click format, you can change the color of what you're typing or what you're drawing. That makes sense. Oh, fancy. Okay. So somebody's saying, wouldn't one of them just be T? That's a good question.
What about that one where it just comes down and kind of bumps the X or the T axis?
Excellent question. What does it mean when you have on a polynomial something come in and hit but bounce off? Doesn't go through, it just bounces off. Anybody know what that's called?
Multiplicity.
Ooh, it's got a multiplicity that is what kind of a number?
An even number.
In other words, it can't be to the first power. That root has to be to an even power.
I didn't actually see that one bounced off.
Here, I can scoot it down so you can see.
Oh, okay. So
So you remember how I said last time that I'm a big fan of using whatever tool is most convenient? If writing it, handwriting it's convenient, awesome. If typing it's convenient, awesome. If using Maple's convenient, awesome. If using something like Desmos is more convenient, then use that. So for example, if I wanted to share what I was working on just a second ago, if I can figure out where the heck it is. Is that my Desmos? Yeah, there's my Desmos. Ah, oh no. Oh no. Ah, quit it. There we go. Uh-oh, what happened to all the... Hold on. Are you guys seeing my Desmos screen? You are, good. Okay, whew. I was worried there for a second. So here is one of your polynomials. What do you think? Does that produce something that looks kind of like what I had?
Honestly, I can't remember what you had.
Okay, well let me show you.
0, 0, right?
Yeah, let me show you. Let me remind you what I had. It was this. So I'm going to switch back over. Hold on.
Was that supposed to be a 0, 0, that dot? Because I kind of saw
I
that
was
as-
sloppy. So if you interpreted it 0, 0, fine. Otherwise, yeah.
I thought it was like a
It's-
little bit farther above.
Yeah, I would say it doesn't look like it is, but so this is the Desmos graph of one of the groups. That looks like it produces something that works for making a f of t versus t graph. That means now if we switch over to Maple, and you have to forgive me while I do this one more time. I'm going to switch over to Maple. Where the hell is Maple? There it is. If we switch over to Maple, all I have to do now is throw in that function. I'm just going to type it in as was foretold. Putting parentheses doesn't automatically mean multiplication to Maple. So just remember you got to
That was
put
my issue.
multiplication signs in between. So that's t minus 1 times t minus 5. And that's raised to the second power. So let's see if this produces what we expect it to. Uh-oh, must be, what did I do? As far as, what did I do? Somebody help me with my error. What did I do wrong? Oh, I forgot to declare my independent or my dependent variable. YFT comma, there we go. Boop. Now, you probably can't see it because it's really damn difficult to see, but these arrows are not all pointing in the same direction. They're down, and then all of a sudden they're up, and then they're down, and then they're up, all the way across here. So if I were to change my vertical settings, make this like 1 to -1 to +1, that might help. And this, actually, no, this is terrible for being able to produce the slope field because those slopes are so extremely large. So let me
So you
stick
made the
a,
y values really large, though.
yeah, that might help. But let me throw a scaling factor in front of this. Maybe that'll help. A little bit. And then if I go 10 to 10. There we go. That's a little better. So we have something that's negative to the left of t equals, it looks like 3, yeah, 3. And then in between 3 and 1, it's positive. And then between 1 or -1 and +1, they're negative. And then between -1, or sorry, between 1 and 5, they're doing all kinds of crazy stuff. It looks like it flattens out right around 5, but it never quite goes negative. It just kind of flattens out and then continues to go up. And that is exactly what we would expect from the graph that we had on that little hand-drawn graph, right? We would expect negative slopes for t values less than whatever that is, positive slopes in between there, negative slopes in between there, positive in between here. It'll hit 0 here, but then just revert back to positive. So here's the question, and this is bringing us home to section 1.6. So if you haven't watched the videos for 1.6 or looked at the notes for 1.6, then this is going to make no sense to you. But what kind of equilibrium point is that right there? Is it a source, a sink, or a node?
A source?
Yes.
So on one side, we have negative, and then on the other side, we have positive, right? What we're going to wind up doing in this today is pulling together our thinking about equilibrium solutions, thinking about autonomous differential equations, of which that isn't one of them. And we're going to be pulling that together along with the key point of section 1.5, which is this existence and uniqueness theorem, this way of guaranteeing that we have a single unique solution through any point on the plane, right? So we're going to pull all this stuff together, and we're going to do that by taking a look at some specific problems. So if you haven't watched the videos for 1.5 and or 1.6 yet, then it's going to be a little rough. I'm not going to lie to you, but I want you to still try and engage with the problems and see if you can make sense of what's going on. So I'm going to stop sharing here. And then what I'm going to do is referring back to the, let me close this window. I don't need that open anymore. Referring back to today's agenda, you should see each one of the teams is responsible for 2 questions. One of them is a 1.5 question, and you might notice all groups are doing the same 1.5 question because I want to be able to talk about it and have everybody get at the same idea. And then everybody's got a different 1.6 question. So I'm going to split you guys up into teams, break you up into teams, but then what I want you to do is work first on that 1.5 problem and see if you can get that taken care of. The existence and uniqueness theorem is not terribly tricky to begin with, right? It's not a super complicated concept, but it underpins so much of what we do that we want to make sure we understand how it works and how it gets used. So do the that problem number 1 from 1.5 first, work with your partners and see if you can come up with a solution, and then transition into the 1.6 problem. Does that make sense? Excellent. Okay. So I'm going to open up the rooms. You guys can disperse.
We graphed y1 of t equals -1 and y2 of t equals 1 plus t squared.
Mm-hmm.
And since those were the only 2 lines, we graphed those on Desmos. We interpreted that the unique solution rectangle, so to speak, existed between those. And since the initial condition was y of 0 equals 0, we figured that the initial condition point was going to be 0, 0 on the graph, and that the rectangle be around it.
So do you happen to have that on Desmos? Can you pull that up for us?
Yeah.
So we can take a look at it. Everybody but Stefan will be able to see it.
Sorry, Steve.
I feel targeted.
No, he was talking to me. Gosh, you're such a persecuted
And discriminated
individual.
against.
Yeah. Well, you know, you got the same name as the instructor. What are you going to do? So Wyatt is currently sharing his screen. And so what we're looking at is essentially two known solution curves on the slope field, right? So imagine the slope field's in the background. We have two known solution curves. So if you were to move, can you plot the point 0, 0 on Desmos? Just parentheses 0, comma 0, close parentheses.
Okay.
Blink. So all we can say about the solution curve is that there's a solution that passes through that point. It's guaranteed to be unique. And what else do we know for certain about where it can go and where it can't go?
So it can be either above the line y equals -1, or it can be below the parabola y equals 1 plus t squared.
But it could never be below the line y equals -1, and it could never be inside that parabola up there.
Right.
And as a matter of fact, it can't touch either one of those two curves, right? Because in order for it to touch one of those two curves, that means it would have to become that curve itself.
Right.
So nice. So if you imagine shading in all the area below y equals 1 and saying, "Thar be dragons, there's nothing down there, you can't go down there." And everything above that parabola, shade that in. Anything that's shaded is off limits for this solution curve. Anything else, it could be anywhere in there, but it's got to pass through that point 0, 0. So the existence and uniqueness theorem guarantees that it exists and it's unique, but because there are these other two solutions that we know, the existence and uniqueness theorem also guarantees, and I like the way you put it, that rectangle can be anywhere in this unshaded region, right?
Right.
The rectangle can be as big as any of that stuff, but it must stay in that region. The solution curve can never go anywhere else. So, wow, nicely done, sir. Excellent use of Desmos too. Handy. Okay, did anybody get a chance to start looking at the 1.6 problems? Because there's a good grab bag of those. Any groups start looking at those? Yeah. Bryce, would you like to talk about your problems?
I'm gonna share my screen real quick.
Feel free.
We had, oh, wrong one. We had 4.
Okay. And so for number 4, it's saying a phase line for an autonomous differential equation, blah, is given to the right. Okay.
So then basically we labeled our source and a sink because the top one, the arrows are going away. It's the source. And the bottom one, the arrows are going in, so it's a sink. And then
So excellent job on labeling and redrawing what's that word I'm looking for? The phase line. So good job on that. The only thing that I would say, and it's kind of it's not required, but it's sort of implied, that I would name each one of them, refer to them as like Y1 and Y2.
Oh, okay. Yeah.
That would make it easier for you to later on refer to it and go, oh, and so you can clearly see that Y1 is a source and Y2 is a sink.
Okay, gotcha.
Yep.
Yep.
And it'll come in handy later for being able to refer to those points on the graph below as well.
Graph, yeah, that makes sense.
So when you drew, that's okay. You can leave it the way it is. That's look at you. Look at you getting fancy. You're going to draw it in there.
So basically, we just kind of moving onto a graph. Like this one came down here, this one came over here, and we basically just said that if it's a positive arrow or going up, that means it has to be above the axis. And if it's going down, it's below the axis.
And by the way, what are the axes for that graph that you're on right
that
now?
I did not label. Is
Mhm.
y in the it's y of t in the up and down, and then t in the x.
So you had me on the phase line, but you're labeling the axes wrong.
Backwards.
No. That graph, that polynomial looking graph, that does not have y versus t.
I
Anybody
have
want
no
to,
idea.
Emma, you want to help them out?
By process of elimination, is it f of y on the vertical and then y on the horizontal?
Ding.
Shoot.
Yeah, because remember those points where the slope is equal to 0, that means the height is equal to 0. So that means this direction has got to be f of y or dy dt. And this direction identifies
Y.
specific y values, right? And this is kind of connecting back to what we started on earlier today. Yay! So I agree with you. Horizontally, it would be y, but in the other
Would I
direction,
mess
it
it
would
up?
be f of y. The vertical direction would
Oh,
be f of
okay. You said this one's f of y?
y. Hmm.
Okay, yeah, that makes sense.
There's one more problem with that graph. I agree with the shape. I agree that it's going to be kind of like a parabola and it's going to have two roots, but I disagree with where the roots are located.
Yeah, I just read it and it said that y is equal to 0. I'm guessing we'd have to.
So reread that sentence, that second sentence.
You can presume that y equals 0 is the exact middle of the segment shown.
So the segment of the phase line. So the exact center of the phase line would be where? Show me on your phase line.
Here?
Yep. And so if that's y equals 0, then
It's
that
gonna be something
axis.
like this.
Exactly. Yes. Very good. Yes.
Honestly, like I didn't even
Oh, no,
read the part that says y equals 0. So
I know. And you'd be surprised. I will occasionally put things in questions because I'm challenging you to read carefully. And already, and some of you who have gotten your papers back already know this, sometimes the single biggest mistake that people make is they don't read the question and they don't answer the question being asked. I'm guilty of this myself. Somebody starts asking you a question and you decide, oh, I know what they're going to ask me, and you just start answering them, and you're like, no, that wasn't what I was asking. What I was asking was this. So make sure that you're answering the questions I'm asking as opposed to the ones that you want to answer. So absolutely.
I do have a question. In part A, it says comment on the relative stability of each
Mhm.
over time, and we weren't really sure what you were looking for with the stability term.
That's a very good question. And I put it in there on purpose. So imagine that you are really, really close to what he's calling F2, the Y2, right? Imagine that
Oh,
you're really, really close to it, but you're not right on the dot. You're slightly above it or you're slightly below it. What's going to happen if I play the clock forward? If you're just slightly above it, what's going to happen to that solution curve over time?
It'll be an underestimate. I don't
No.
know.
So remember what the let me see if I can find here. Let me steal the screen sharing. Let's see if I can pull up Maple. And I'm gonna have to make a new one, I think. Yeah, I'm gonna have to make a new one. So let me do a DE plot. Oops, come on. DE plot. And then I'm just gonna borrow this because I'm lazy. And rather than this differential equation, I'm going to make an autonomous one. So let's go with something really simple like y plus 1 times y minus 1. Really, really simple. Uh-oh, what did I do? Oh, y of t. Yeah, sorry, it was supposed to be y of t. It's yelling at me. of t, and we don't need to go all that far. We can just go from like -2 to 2, -2 to 2. Okay, so I have now a nice, pretty autonomous differential equation. Well, how would you describe this this equilibrium solution located at y equals 1? So I'm gonna draw both of these equilibrium solutions in here. Get my line color. So you can see I have two equilibrium solutions, right? How would you define this equilibrium solution? Is it a source, is it a sink, or is it a node? And anybody can answer.
It's a source.
It's a source. Good job. You guessed right. You had 1 in 3 chance and you guessed right. How do you know it's a source just looking at it?
Because they're going away.
So as time goes by, as t gets bigger and bigger and bigger, a solution curve is going to move away from that equilibrium. Now, if it's exactly on the equilibrium solution, it doesn't move away from it at all, right? It's just the equilibrium solution. But if you're slightly above it or slightly below it, you'll start to shift away from it. And so this is why we would call that equilibrium solution unstable. Because as time goes by, if you're right around that equilibrium, you take off from it. Guess what we refer to this equilibrium solution as in terms of stability?
A sink.
It's a sink. In other words, if you're just above it or just below it, if you start off with an initial condition up here, so I'm going to create a new initial condition. I'm going to call this one y of 0 equals, I want something that's just above this initial condition. So give me a y of 0 equals, what does it have to be? Give me a y coordinate that's just above this guy down here.
Like 3 divided by 4.
Okay, negative 3/4. Okay, and sure enough, I wind up with negative 3/4 right here. That's the unique solution that passes through this point. Now notice, as time goes by, as I move to the right on this graph, what's happening to my solution curve?
It's approaching that equilibrium solution.
It gets closer and closer and closer to it. In other words, it's like the equilibrium solution is sucking all the solution curves around it in towards it. That's why we call this a stable equilibrium solution, because everything around it wants to become it. And up here, everything around this thing wants to get the hell away from it. So if I did something like another initial condition, like y of 0 equals something just slightly above this. So like 1.01, just a tiniest little bit above this equilibrium solution up here. Maple says, oh yeah, it's going to be really close to it here, but over time, it wants to run away from it. So this solution up here is what we would call unstable. Everything around it wants to get the hell away from it. You probably have people in your life who are unstable. And what do you want to do when you're around those people who are unstable? You want to fix them. That's right, because you're wonderful humans. No, you want to get the hell away from them, right? Ugh, get away. So equilibrium solutions are like people. The stable ones, everybody wants to get with. But if you're not, then, get away, get away.
So in general, can we say that a source is unstable and a sink point is stable?
Bingo. So here's the
Okay.
question. What about a node? How can I turn one of these two equilibrium solutions, how can I turn it into a node in my DE plot? What could I do to my code to turn one of them into a node? Hey, that rhymed.
Well, a node is just when they're both going in the same direction, right? On both sides
Correct.
of it.
So it'd have to be going up here and up in between. So how could I change one of these two to turn it into a node? I'll give you a hint. It has to do with multiplicity. Come on, Chris, hook me up.
Would it have to have just an even multiplicity?
Let's try it. Let's see. I'm going to raise the second one to the second power. Take a look at what happened. Take a look at what happened to my y equals 1 solution. I now have things above it. If it starts off above it, it's trying to get the hell away from it. But if you start below that solution curve, you're trying to get with it. In other words, anything down here over time will eventually approach y equals 1. Now, if you're wondering, this guy right here, that initial condition, that's still there, but it's so subtle, it's such a small increase that I would have to extend my graph. I'd have to extend my window out more. So let me see if I go from -2 to 10, you should be able to, oh wow, you still can't see it. Go -2 to 20. Oh no, why am I changing the y coordinates? It's not the y coordinates I'm trying to change. It's the t coordinates that I'm trying to change. Silly me. If I go out from -2 to 10, still can't see it. Oh, look at that. That's crazy. -2 to 20, still can't see it. Where the hell is it? -2 to 50. There it is. See it right there? It's really, really subtle. It's almost exactly the equilibrium solution. Then enough time goes by and then it takes off. And as a matter of fact, we even get an error saying, oh my God, after this t coordinate of like 48.67, it basically behaves like a vertical line. And of course, Maple, just like most graphing calculators, freak out when they try to graph something and it goes vertical. But by changing the multiplicity on one of its equilibrium values, I can change whether it's a source, a sink, or a node, right? So if you haven't watched the videos for 1.6 or 1.5, you definitely need to get on that. You've got a problem set to work on. You've also got an investigation to work on. I was hoping to give you guys a little bit of time before we split off today to work in your groups and take a look at the investigation. But there's one more thing that I want to show you. It happens to be in Maple before we get too far. Let me kind of, in Maple, let me undo some of this gobbledygook here. So imagine instead of knowing this number is 1, what if we made it A and this one A? What do you think will happen if I hit enter and ask Maple to make me a slope field? What's Maple gonna say? It's okay, you can guess. If you're wrong, we'll find out momentarily.
It's going to say yes.
It's gonna say, yes, let's do it, says the guy who can't even see what's happening, right? But I replaced one of my parameters in the differential equation with a variable. Essentially, it's gonna look at it and see it as a variable. Maple says, I don't know what the hell you want me to do, but I don't know what to make of this A thing. If you haven't defined it somewhere else in the document as being a numerical value, it's not going to know what to do. But rather than hit enter, if I kind of put my cursor back on this and then I right click, and I'm saying this out loud so that Stephen can understand, but also so that later on you can go back and watch this. If you right click, one of the options is explore. And explore is the equivalent of, those of you who have used Desmos a lot, it's like making slider bars. So if you click on explore, it's going to pull up a window. It's going to pull up a window. There it is. Whew. And all of the things that are in the DE-plot command that could possibly be parameters, variables, are going to be up there. And so notice, A is one of them. The color blue is one of them. T, Y, line color. Maple's just like, hey man, whatever you want to make a slider, you just let me know. And so I don't really care about the blue or the T or the Y. The T and the Y, those are the variables of interest. And the line color, I want a slider bar for A. And I want A to go anywhere from -2, or actually, I'm just going to make it go from 0, would be the smallest, all the way up to 2. And I'm going to make it just 2. And you'll see what happens when I just make it 2. Hit explore down at the bottom.
I don't think we can see the window.
Oh, you can't see the, well, you can recreate it. And you can't
Okay.
see the window? Okay. You can recreate it. You'll see the slider bar options pop up. I'm sorry, you can't see that. But now look what happened. I now created the DE plot, but down below there's a slider bar that I can drag and see what happens when A changes values. So when A equals 1, we get exactly the same DE plot that we were just looking at before, right? So it's y minus 1 times y plus 1. Big deal. But when y equals 0, this becomes the DE plot. It looks very different. So being able to do it with the slider bar allows you to literally explore what happens in the command. Explore what happens with the DE plot. Let me do one more thing. I'm going to go back up here and I'm going to hit explore as an option. And unfortunately, you won't be able to see it, but I'll describe what I'm doing. I hit explore. And then again, I'm going to click on skip for all the things that might vary, things like the color blue, the T, the Y, the line color. I don't want those to be slider bars. I only want the A to be a slider bar. And so I'm going to make the values, there's a little box for what's the small end, dot, dot, what's the upper end. And so I'm going to make this go from 0 to 2.0. I'm going to use a decimal in there. And when I do that and I hit explore, notice the difference in the slider bar. Now when I slide, it's not just 0, 1, and 2, it's now 1 decimal unit in between. And so I get a better, kind of more interesting way of looking at this DE plot. So when my A value is 0.8, I get a solution curve that kind of looks like this, or a DE plot that looks kind of like this. Interesting slope field. And as I get closer and closer to an A value of 1, it starts looking more and more like the thing that we saw before. And as soon as it goes beyond 1, it starts looking different again. And so with this, you could create all kinds of interesting slope fields just based on a basic differential equation. And you could vary the parameters in it. And you can have as many parameters as you want. It gets kind of confusing when you have like 10 parameters that you're using slider bars on, but you could if you wanted to. So for example, if I went back up to the code and I said, in the code, y of t plus a for the first factor, and then y of t minus b for the second factor, and then I can click on that and say explore, and then I'll make a and b both slider bars, and make each one of those go from 0 to 2.0. I don't know why 2, it just sounded good. And then I hit explore, and now we have the ability to vary the A, like we did before, but we can change the B separate from it. And so we can make some interesting graphs this way. And there's a couple of pieces on the homework, on the classwork, where I say, use the explore feature in Maple. I want you to be able to use the explore feature. So this is a kind of an introduction to it. It's not the only time we're gonna run into it, but anything that you can type in as a code, as a calculation or a request for Maple, you can ask it to explore with slider bars if you want. So it's kind of handy, right? So if you want to do a desolve on equation and find out what happens if you change this quantity, you make it a little bit bigger, you make it a little bit smaller, make it a parameter, and then use a slider bar to wiggle it around and see what happens to your solution. So any questions on the Explore feature? I want you to try it out, give it a shot, see how it goes. No questions on that? Cool. Well, I'm wary of the time because I know it's after 8 o'clock. So thank you very much for being patient. You have some homework to work on. You have a problem set that's going to be due next time for sections 1.4, 1.5, and 1.6. That problem set covers those 3 sections. You have some classwork that you can look at. We've gone over some of the problems today, but not all of them. And I strongly suggest that you check out those classwork problems in case you don't have anything else better to do this weekend. But you know how to get a hold of me, multiple ways of getting a hold of me, and you know how to ask questions. So please, please work on this stuff. And don't wait until Monday morning to start working on the homework. It doesn't give you enough time. You really need to process this stuff, right? So what I'm going to do right after class tonight, I'm going to make sure these videos get uploaded, but then I'm going to start working on the videos for 1.8 and 1.9, which are 2 more sections that I want you to watch before we get back together on Monday. So, and now that I've got my computer situation sorted out, I should be able to make those videos and have those posted by probably later afternoon tomorrow. Shouldn't be a problem getting those done. And I'll send out a remind to let people know that that's what's going on. So we've covered a lot of ground today. We've connected a lot of pieces together. What I want you to do, you got to kind of sort the mess out. Some of you have some videos to watch and some notes to fill in, but you all have problem sets to work on, and you all have teams that you can talk to and work with. So make sure that you're working together on this stuff. And don't be a stranger. If you need something, shoot me an email or, send me a text, smoke signal. Just making sure you're paying attention. Smoke signals, not legitimate. Unless you tell me what direction to look, and then I can do that. So, Chris, you're probably the closest to me. So yeah, I think you could probably do smoke signal. I think you're probably like 2 miles away. So I think you could do smoke signal. But otherwise, if you need me for anything, you want to ask questions, you can stick around. Otherwise, I'm going to hit stop recording the Zoom meeting, and Mass is ended. Go in peace to love and serve mathematics. So see y'all later. Hey, the Catholics in the audience got that joke. Okay. See y'all later.